Graphene consists of many identical benzene rings of carbon atoms bonded infinitely to form a two-dimensional honeycomb lattice. This structure gives graphene its high optical transmittance and its low electrical resistance, making it an ideal material for transparent conductive electrodes which are used in optoelectronic devices. However, such applications require large area and high-quality graphene films. Graphene films comprising of monolayer and few-layer graphene with low defect density can be produced by the chemical vapor deposition (CVD) of a volatile hydrocarbon on a metal substrate, but there are difficulties in transferring these films onto other target substrates after growth. This is because the conventional transfer method is ideally effective only if the graphene films are perfectly flat. However, during CVD growth, the metal substrate undergoes surface reconstruction at high temperatures. The graphene film that grows along the metal substrate will be uneven. After growth, the uneven film does not adhere flat on the smoother surface of the target substrate, and unattached areas of the graphene film can break away easily. The main problem is that the PMMA layer is a hard coating, and the adhered graphene film is unable to relax even when the PMMA is removed. The transfer method can be improved by introducing a second PMMA coating because the liquid PMMA solution can dissolve the pre-coated PMMA layer to relax the graphene film. This project compares the optical transmittance and electrical resistance of both monolayer and triple-layer graphene films prepared with the conventional and improved methods. 8 samples of half by half inch PMMA graphene copper films are prepared on 1 by 1 inch glass pieces, 2 samples of monolayer graphene and 2 samples of triple-layer graphene for each method. The PMMA graphene copper films are prepared by CVD and the glass substrates are cleaned by sonication. The PMMA graphene copper films are immersed in ferric chloride solution for 40 minutes to etch away the copper layer. The remaining PMMA graphene films are immersed in deionized water for 10 minutes to remove the ferric chloride solution. This process is repeated 5 times before each PMMA graphene film is lifted with a glass piece and dried on a hot plate at 85 degrees Celsius. For the conventional method, the PMMA graphene glass films are submerged in acetone for 30 minutes to remove the PMMA layer. For the improved method, the PMMA graphene glass films are spin coated with 950 gram per mole PMMA before they are submerged in acetone for 30 minutes. The graphene glass pieces are dried, and this process is repeated twice for triple-layer.
The optical transmittance of monolayer graphene prepared by both methods is 97%, while the optical transmittance for triple-layer graphene is 91 to 92%. This shows that the improved method does not increase optical transmittance. The electrical resistance of monolayer graphene is generally higher than the electrical resistance of triple-layer graphene. This may be because defects in one film can be bridged by its neighboring films in triple-layer graphene, thus decreasing resistance. The improved method increases electrical resistance of monolayer graphene because the 2 coatings of PMMA take more time to dissolve than a single coating, resulting in many spots of PMMA residue on the graphene films. Figures 1 and 2 show that the improved method leaves PMMA residue on all graphene films, hindering electron flow. On the other hand, figures 3 and 4 show that most graphene films prepared by the conventional method are complete, though there are some incomplete ones with regions of graphene broken away. Overall, the improved methods increases the electrical resistance of monolayer graphene. However, the PMMA residue in triple-layer graphene can be bridged by neighboring films, creating electron pathways and decreasing electrical resistance. The conventional method may further damage triple-layer graphene during the repeated transfers. As a result, the improved method decreases electrical resistance for monolayer graphene. The conventional and improved methods give similar optical transmittances for both monolayer and triple-layer graphene. The improved method increases the electrical resistance of monolayer graphene, but it decreases the electrical resistance of triple-layer graphene. Graphene films prepared by the improved method have a lower density of cracks and tears even though there is contamination from excess PMMA. Optoelectronic devices typically use few-layer graphene, hence we can conclude that the improved method is a better choice for industrial use.